notes for AP Calculus on the topic of the divergence, also called the nth term test, the p-series test, and the integral test. So these say determine whether the series converges or diverges and specify what tests or tests you're using. So, first one that you can apply easily is the divergence, also called the nth term test. And all these series you can see are infinite due to the infinity there. This just means to get the first term you would substitute in 1 for n. To get the second term you would substitute in the next integer 2 for all the n's, then 3, then 4, and then add up all those terms forever to go on to infinity. And this formula here that allows you to find the nth term is referred to as a sub n. Because if you plug in 1, it's a sub 1 the first term. If you substitute in 2, it's a sub 2 the second term, and so on. So to find it, use the divergence test, you can do this by just finding the limit as n approaches infinity of this formula here that allows you to find each term a sub n, in this case 5n minus n cubed over 4n cubed plus n squared. And remember, with limits in infinity, just polynomials like this, you can just look at the term on the numerator and denominator with the highest exponent, a degree. So in the numerator, that's going to be the infinity to the third, and on the denominator, the 4 infinity to the third. And then you can see those infinity cubes completely reduce out, which leaves you with just negative 1/4. And the divergence test can never guarantee that it converges, but what it can do is it can guarantee that it diverges if this limit is not 0. In this case, it's negative 1/4 not equal to 0, so that tells us this series diverges by the, you can either call it the divergence test, sometimes it's referred to, or it's oftentimes, especially on the AP test, referred to as the nth term test. If this was 0, then what that would tell us is that it might converge. It has a chance to, and then we'd have to use one of the other tests to determine if it actually does converge or not. So divergence or nth term is really nice for just quickly figuring out ones that diverge because the limit is not 0. All right, let's take a look at the next one. So in this one, just like with integrals, this is similar, the summation here, it's similar to the concept of the integral. The difference is these are finite terms. We're only substituting integers. So we're just substituting 1 for n, then 2, then 3, then 4. Where the integral covers all the values, not just the integers. But it's a similar concept there. And like with integrals, constants that are coefficients, like the 5 here, can be pulled outside the sigma notation or the sum as well. So we can pull the 5 out in front like that. And then what we're left with is 1 over, and if we put this in fractional exponent form, n to the 2/3. So you can see this one, you could use, sometimes there's more than one test that you could potentially use to determine if it converges or diverges. So if we wanted to use the integral test, then you could write this as n to the negative 2/3 and integrate it. It wouldn't be that hard to figure out. But this one's actually a little easier if you just notice this fits the form of the p-series test, where p is the exponent on the denominator, p is equal to n, p is equal to 2/3. And since that is less than or equal to 1, that guarantees with the p-series test that this series diverges. By the p-series test. Whereas if p here, this exponent was greater than 1, then it would converge by the p-series test. So if it does fit a p-series, it will tell you, unlike the divergence or nth term test, it will guarantee if it fits that form that it diverges in this case, or sometimes that it converges. All right, let's take a look at the next one. On this one, It can also fit the p-series. It's a little trickier to see that here. Notice again, you can pull out the 2 out in front. And then in order to make this fit a p-series, we've got to combine these. So this is n to the first, and this is n to the 1/2. And when you multiply those, remember with the same base, you add the exponent. So that's 2/2 plus 1/2. That's n to the 3/2. Now it fits the p-series once we combine it. And this time we can see p is equal to 3/2, which is greater than 1. So this time, because the value of p is greater than 1, this guarantees it converges by the p-series test. And again, converges just means when you add up all these terms that go on forever to infinity, it's going to actually approach a specific number. Versus the diverges ones means oftentimes it will go to infinity or it will bounce back and forth. It will never approach a specific value. Okay, so those are the different ways you can use the p-series test. Let's take a look at a couple more. So on this one, notice it doesn't fit a p-series because the n is up in the exponent, not in the base here. So even if we can't use that here. So this one though can be fairly easily integrated. Again, this is similar to the integral. So when you use the integral test, you rewrite it. Integral, wherever n starts at, that becomes your lower limit, and the infinity becomes your upper limit. And then we get an improper integral, and we've got e to the negative n dn. So I'm just going to use n here, the same variable. If you really don't like using n, you could use a different variable like x or something and get the same result. But I think it's easiest to just use the variable that's already in there. So this one we can integrate. Normally you'd set u equal to negative n, but you can use the u substitution shortcut since the derivative is just a negative one. When you integrate, remember e, just like we did there, stays the same. By using the u substitution shortcut, since the derivative is -1, you would divide by that derivative, -1. And then it's evaluated from 1 to infinity. And then to make it simpler, you can pull out the -1, the coefficient out in front. And then you can rewrite this as 1 over e to the n if you want to make it a little simpler without the negative exponent. And then substitute an upper limit of infinity, so we get negative on the outside. Then when you plug in infinity, you get 1 over e to the infinity minus 1 over e to the first. Or just 1 over e. So 1 over e to the infinity right here. Well, with infinity there, that's 1 over some huge number. So when you have infinities in the denominator there, 1 over that, that's going to approach 0. So then all we're left with is -1 out front times -1 over e would be equal to +1 over e. And since we got a specific number, what the integral test says is, since we get a specific number here, that means this converges. And if the integral converges, then the series also converges. Or if the integral diverges, the series also diverges. This is how the integral test works. So it doesn't guarantee the series adds up to be 1 over e, okay? But it guarantees that since the integral converges, so will the series. So this one we can say converges by the integral test. Let's take a look at one more. This one, again, you can see it doesn't fit p-series because we've got that natural log in there. So this one may not be super obvious, but you actually can integrate it. So 2 becomes the lower limit there, and infinity is the upper limit. And we have 1 over n times the natural log of it. So this one doesn't really fit the, although it kind of might look like integration by parts one, it doesn't really fit that, because that requires things multiplied together and the natural log is on the denominator. So it wouldn't really make sense to have one of them being 1 over natural log of n and then n to the negative 1. That's not going to work well with integration by parts. But it actually just works if you use u substitution. There's not many things that say u equal to. If you set equal to the entire denominator, like sometimes it works, then you have to use the product rule. It's going to make it too complicated. But if you just set u equal to just the natural log of n here, then let's see what happens. Be careful with the n there, there's a lot of n. It can be a little confusing there. So if you prefer to use a different variable, feel free to do that. So du dn is 1 over n. Here we can't use the shortcut because the derivative is not just a constant. And if you cross multiply, you get 1 times dn. dn equals n times du. And since we're not using this, we're using regular u substitution, we've got to convert our lower and upper limits there. So when you plug in infinity, that's the natural log of infinity. And again, this is infinite, so sometimes this natural log may not matter, but just to be on the safe side, it occasionally might, we'll just leave it natural log of infinity. And then when you substitute 2, that doesn't simplify. That's saying e to what exponents 2, just a decimal number there, so we'll just leave the natural log of 2 to be exact. And then we've got 1 over n, and then we just replaced the natural log of n with u. And then we can replace the n with n times du. And then notice what happens, the n's reduce out, which is what we want. And all we're left with is 1 over u du, which you can integrate to be natural log absolute value du. And since we converted the lower and upper limits already, there's no need to plug this back in for u. We can substitute these in directly in for u. So when you substitute in natural log of infinity, so it would be natural log, absolute, this is already positive, so natural log of infinity, minus the natural log, 2 is already positive, of the natural log of 2. Oops, sorry, I forgot to write the natural log of 2 there. So I just wrote 2. So natural log of natural log of 2. Well, natural log of natural log of 2, that's just some specific number. However, this one, natural log of infinity is infinite, and then you have another natural log of infinity. So this is actually infinite there. If you think about the graph of natural log, you can see why. It does grow fairly slowly due to the shape of its graph here, the basic natural log graph. When you substitute 1, natural log of 1 is 0, because e to the first power is 0, and it looks, there's an asymptote, you can't plug in negative numbers into natural log. It looks something like this. So notice when you head off to infinity over here, it does go to infinity, even though it grows rather slowly, it does keep going up forever there. So because this one is infinite, that's what tells you we don't get a specific number for the integral. That means the integral diverges. And if the integral converges by the integral test, that means the series would also diverge. So this one diverges by the integral test. And that concludes the notes for AP Calculus on the topics of the divergence nth term test, the p-series test, and the integral test continued.